Good afternoon, everybody, and welcome to the webinar on production and utilization of green hydrogen, arranged or coordinated by our Mumbai chapter, INAE, and head office. So, Indian National Academy of Engineering head office has provided us this platform, so we are sincerely thankful to them. And we have 6 panelists today. As per the sequence of presentation, they are Shri Kalyan Bhanja from Wawa Atomic Research Center, Professor Prakash Ghosh from Indian Institute of Technology, Mumbai, Dr. Shriniwas Rao from Wawa Atomic Research Center, Dr. Sudarshan, Wawa Atomic Research Center, then Professor G.D. Yadav from ICT, and we have Suman Chowdhury, NMRL, DRDO. So with this 6 panelists, the whole program will be moderated by Dr. Grover. Next slide, please. Yeah, we request all speakers to present technologies developed by them in 15 minutes. We will have questions after all presentations, after completion of all presentations. And to avoid transmission problems, one set of presentation may be forwarded to INAE head office in advance. Lectures will be recorded if there is no objection from the speakers. So if there is any objection, you can tell in advance, otherwise it will be recorded. And for the audience, during the question answer session, please type your question or comments briefly and precisely in the chat box to ensure that your question or comments are visible to the speakers. Next slide, please. Yeah. So Dr. Grover will be moderating this session. He is a known personality here on this platform. He has already moderated many sessions. So just to give a small introduction, he is an Emeritus Professor in Homi Bhabha National Institute, HBNI, and a member of Atomic Energy Commission. He is a recipient of Padma Shri in 2014. With this small introduction, may I request Dr. Grover to take over for the further proceedings. And at this moment, I also introduce our platform partners, Colonel Shobit Rai from INAE head office and his team. So we are sincerely thankful to them for providing all the supports. Over to Dr. Grover, please.
Thank you, Shashwati.
Most welcome.
Many of you must have listened to the panel discussion organized by Pune chapter of INAE about 1 year back. So I found that a lot of work has been done by various institutions in Mumbai region. So it is time to organize a panel discussion here itself. Rather, I was triggered by to think in that direction by the guest editorial written by Professor Yadav in Current Science. And thank you, Professor Yadav, for that. So let me just briefly introduce the subject so that all of you don't have to repeat and you can straight away come to technologies. Climate crisis calls for use of low carbon energy sources. All countries around the globe are concentrating on decarbonizing the electricity sector, replacing petrol and diesel driven light motor vehicles and two-wheelers have also been prioritized by governments around the globe, but this is not enough. Fossil fuels are also used in making iron and steel, in making cement, different chemicals, shipping, aviation, and trucking. To achieve the goal of limiting temperature rise to 1.5 Celsius, energy professionals have to think in terms of decarbonizing energy sector and not just the electricity sector. Now, IPCC in this regard has recognized hydro, nuclear, solar, and wind as low carbon technologies. solar and wind are intermittent sources. As their presentation in the grid increases, the challenge of balancing the grid is becoming bigger and bigger. Importance of hydrogen lies in the fact that it can be used to replace fossil fuels in industry and also be a part of the solution to balance the grid. This is a very important role for hydrogen in future. Like electricity, hydrogen has to be produced, and considering the challenge posed by the climate crisis, it has to be produced by clean processes. Such sectors as chemicals already use hydrogens, and that is produced mostly by steam refining of methane, and that is not a clean process. To have an idea about the magnitude of the task before us, one can examine the requirement of steel making. The government of India plans to raise steel production from 111 megatons at present to 300 megatons by 2030. And the data from Europe indicates that for making 1 ton of steel, one needs 50 kg of hydrogen. And of various methods for producing hydrogen, steel electrolysis looks very promising. And one can easily have an efficiency of 70% or maybe even 75%. And looking at the calorific value of hydrogen, an efficiency of 70%, one needs about 56 kilowatt hour to produce 1 kg of hydrogen. Now, based on this, one can calculate the requirement of electricity to produce hydrogen, but this calculation is not straightforward. One also has to know the usage of scrap, electric arc furnace, etc. And different people have given different estimate, and for India to produce 300 megatons, it translates to about 300 to 800 terawatt hour of electricity per annum. And to put this number of terawatt hours in perspective, let us recall that in 2021, India generated 1600 terawatt hour of electricity. So this tells us the magnitude of the task before us, magnitude of the capex which is required for this purpose. Let's now talk about transport sector. For light vehicles, that is for city transport, it will be prudent to use electrical vehicles as there are energy losses from electrolyzers to the wheel. However, for trucking, one may have to use hydrogen. Of course, in this case, from countries like Germany, there is an alternate viewpoint that a truck driver has to take rest every 4 hours. So one can provide infrastructure on highways where when he's taking rest, he can charge the vehicle. In India also, there's an initiative which has been taken by NMRL in this regard. This has resulted in the development and demonstration of IC engines based 2-wheelers, 3-wheelers, minibuses that run on hydrogen. And 2 hydrogen refueling stations have been established, one in Faridabad and second in Gurugram. For decarbonization of aviation, several paths are contemplated, including the use of biodiesel, ethanol, and hydrogen. Biodiesel derived from palm oil was preferred at one stage, but considering large-scale deforestation in Indonesia, several major economies have decided to phase out biodiesel over the next years. Hydrogen can be used in fuel cells to produce electricity for short-haul flights, or it may be combusted to power gas turbine. Of course, for shipping, hydrogen is the only solution. So if I summarize, we have to decarbonize energy sector and not just the electricity sector. The importance of hydrogen lies in decarbonization of the energy sector, as it can decarbonize industry, heavy transport, shipping, and aviation. And to achieve this, we have to produce hydrogen in bulk, and that is why this panel discussion today. So we request the panelists to speak about their technologies for the production of green hydrogen under development in their laboratories, cost of production wherever they can provide, requirements of capital expenditure, use of intermittent sources of electricity, influence of intermittency on the cost of production, fuel cell development, hydrogen storage, transport, and any other issue which they think is relevant. Since time is short, I request all speakers to focus on technology development in their laboratory. Thank you. Now, can we go to the next projection? So the first speaker is Mr. Kalyan Bhanja, who studied chemical engineering in REC, now in NIT Durgapur, and joined Heavy Water Division BARC after completing training school, orientation course in nuclear science and engineering in training school. And he was involved in the development of technology for hydrogen isotope and successfully developed multi-component chemical exchange and distillation models for hydrogen isotope separation. The indigenously developed high-efficiency structured packings used in distillation columns are workhorse for heavy water production. He is a key member for the development of high-purity crystalline and polysilicon production technology, which is at advanced stage of demonstration. And he is leading a team which has successfully developed indigenous alkaline water electrolyzer for simultaneous production of high purity hydrogen and oxygen. He has received awards and he will speak on electrolytic methods for water splitting for the production of hydrogen. Kalyan Bhanja, please, over to you. Maybe he will like to share his presentation.
Yeah, we need to share the presentation. Yeah, thank you. Sir, it is visible, no?
Yes, it is visible.
Yeah. Good afternoon, and thank you, INAE, for giving us an opportunity in this production and utilization of green hydrogen production in Mumbai chapter webinar. So my task is to talk about electrolytic hydrogen production. Honestly, I thought it is a half-an-hour presentation, so we have prepared accordingly. But as Roy Madhav told, that we have to cut short something. So already Ghosh has told so many things. So probably a lot of slides I can skip. Actually, I will skip few slides. So outline is like that. This is alkaline water electrolytic introduction. Then alkaline water electrolyzer, then pure water electrolyzer using ion exchange membrane, then high temperature steam electrolysis, and of course conclusion. This slide is already talked by Ghosh, so I'll skip this slide. And this is typical cost of production today. So what I want to say that this global hydrogen production as on today, electrolytic percentage is only 4% compared to other fossil fuel sources. And as a utilization in India or in globally also, is total for hydrogen utilization for transport is less than 10% even. So as a comparison for hydrogen energy, their only competitor is as a energy carrier is battery. And of course, that is due to their advantage of this efficiency. But of course, for high temperature or high work requirement or high energy requirement, they are not suitable for that. Hydrogen energy is the only suitable thing. Now here, this green hydrogen production, I'll be talking only on the electrochemical production of hydrogen. And that too, all the three systems, that is alkaline electrolyzer, ion exchange membrane electrolyzer, and steam electrolysis, BRC is working on that. And out of this, first two are already matured, and people are talking about only these two technology for green hydrogen production at present. So these are different. What I want to say is this pure water electrolysis and other methods, that is alkaline on PM or anion exchange membrane or steam electrolysis, though overall reaction is same, but internal these reactions are different. Cathodic and anodic reactions are different. So things has to be engineered according to the requirement based on this particular process. So this is the basic input is water and this electricity, and the utility is chilled water. Then we will get hydrogen and oxygen as a product of electrolytic plant. Now development stage, there are whatever we have done. So we have developed alkaline water electrolyzer at industrial scale up to 10 nm³ per hour hydrogen production, corresponding around 5 nm³ per hour oxygen production. There the main thing, there are three aspects. One is design, then this electrode and this membrane. So for design aspect, we can see that earlier there was unipolar electrolyzers where in a cell there is single cathode, single anode, and these are almost Second World War century, that kind of technology. Now it has changed to this filter press type design, which is very, very compact. Here the thing is, same electrode is acting as an anode in some cell, and other cell it is acting as a cathode. So there is huge advantage of space basically, and we can go for very high current density, this kind of configuration. I'll come to this later. And regarding this electrode development, there are electrodes. First is material, another is their configuration. The material, whatever possible electrodes are steel, of course they have to coat it with nickel, then pure nickel is possible. And then platinum electrode are used, but they are very, very costly, and it is not economic to use for this alkaline water, at least platinum electrode. And regarding configuration, earlier this plate type, here current density is very low. To increase the current density, some extended surface kind of thing is thought. That is also possible configuration, but actually the space requirement is more. To avoid these difficulties, the latest methods are this porous electrode as well as perforated plate electrodes. They are having strength, they are having its own advantage or disadvantage. Here they are having good strength. Here they are having very good surface area, very compact design. Second is this electrode membrane development. We have started with asbestos membrane. Now we are slowly moving towards the better this environmental friendly polymers, that is polysulfone based membranes. The most widely used industrial membrane is zircon. So we are also working on that, and to some extent we have got some success on that, and we'll be showing that later on. And this anion exchange membrane can replace this polysulfone because they are hydroxyl ion carrier, so they can also be used. But of course, right now we are not working in this activity. And with this kind of porous nickel electrode and this polysulfone or asbestos membrane, we can go up to 10,000 ASM current density. Though right now we are operating something 5,000 ASM or so. So what is about the fabrication method of this electrolyzer? First, I told we have to fabricate this membrane. Then electrode. Electrode is fabricated by the spray coating of nickel solution. Actually, nickel is suspended in some solvent, and as well as some binder is there. And after that, there has to be sprayed on a nickel wire mesh and sintered in a furnace to make a sheet kind of a. Then they are shaped or cut into pieces, and finally they are assembled in the cell module. And this is the final cell module assembled condition. 2 cell modules are shown here. Each cell module is containing 25 cells each, and each cell production capacity will be something for this kind of 0.5 meter diameter cell. This will be around 200 liters per hour, that kind of production. What we have achieved is this nickel electrode, which is around 1 millimeter thick, and total same assembly with actually it is written 1 mm, that includes diaphragm. This is diaphragm thickness. It is actually 0 gap. And the current density you have achieved up to 5,000 ASM, and total length is not more than 0.6 meter of each 25 cell. Then next is after electrode, this diaphragm development. For diaphragm also, the benchmarking is the bottom line is this is the asbestos diaphragm, which is having best performance, lowest cell voltage for a particular current density or current. Now, when we have tried to replace this with this is a commercial zircon, which is very close to asbestos membrane, but yet there is little bit inferior quality compared to asbestos membrane. Now, when you have started from the top line. That is the zircon equivalent when we have tried to replace that asbestos membrane with our own zircon equivalent membrane. Now we have reached to very close to this, almost near to whatever imported zircon we are having. So of course some more improvement is there, some sizing has to be there, some capacity enhancement is required, but at least performance wise we are close to imported zircon right now. So we have developed all the components of a cell module which is required for a electrolyzer fabrication, and we have started with a very small size, that is 2-inch diameter cells, and single cell, the capacity is something 4 normal liter per hour. Then we have seen the stacking effect here. 3 cells are stacked together. I have shown there is no reduction in performance. Still, it is simply 3 times production, that is 12 normal liter. Then in between some modification was there. Finally, we have reached here. That is a 25 cell module, half a meter diameter, almost 0.6 meter length, and capacity is something. Each cell module is having 5,000 normal liter of hydrogen production capacity. As it is shown, some model is shown how they are working. This is the cell module. Other is we are calling is the balance of the plant. Balance of the plant is very conventional chemical engineering. So we are basically concentrated on this cell module itself. The rest of the things are easily affordable. All the Indian companies are fabricating that kind of thing. Now, if we compare with the global comparison, our cell module, we can say they are at par with the global. There is not at all any impurities there. In fact, we are having very high current density compared to the other electrolyzer available in the market. These are from Italy, this Norway and North Slido, this electrolyzer comparison, this is Teledyne. And the cell voltage, that is the main thing, that is the basically shows how much cell voltage is required for particular current density. They are also almost similar to other electrolyzers. In fact, there is little bit lesser cell voltage, but of course their current density is much lesser and at higher temperature. So the optimum condition as on today is, if it is very good cell, if it is per cell voltage is something 2 volt or less, there we are in this business basically. Now, for green hydrogen, one thing is required, it has to be connected with a green energy source, that is renewable energy source. Of course, today the best thing is solar. The problem with alkaline electrolyzer is this turn down ratio. Their turn down ratio, people are talking, it is very less, so that it cannot be hooked up with directly with the solar PV module, because it cannot work with this variation during the daytime itself. In the season there is even daytime itself there is a lot of variation in the cell voltage or produced cell voltage from the PV cell. But we have integrated our this single cell module with a PV cell, and we have seen that we have achieved something around up to 25% turn down ratio. It is working fine. It is giving the simply ratio wise the same amount of hydrogen as per the input energy whatever we are providing. So that way it can take up little bit variation of this input energy, which is must for this green energy, green hydrogen production. There are little bit advantages if it is a PEM type of electrolyzer. And there is some smaller development for this lab scale electrolyzer production. This is something plug-on kind of thing. We should switch on and we should get the hydrogen, and it should be very high quality. I mean high purity, as well as a little bit at reasonable pressure. Whatever we have achieved so far is around 4 NLPH hydrogen production at 3 bar pressure. Our target is something we have to increase the cell size, but before that we want to increase the pressure, which is normal requirement for any laboratory. So we are very close to that. It is under final stage of development, we can say. And further, rest of the thing is packaging. This is CIC and PIC module. There we can show the basically internal cell is cylindrical cell only, or it can be planar also, but here they are both are using cylindrical cell, and only packaging is the difference that we can achieve with the same cost or something. The next is PEM membrane based electrolysis. BRC is working on this also, and here there is some development. Here also main thing is that membrane, that is as on today, whatever Indian PEMs are fabricated or in the market, they are using Nafion membrane, which is as on today imported. So our intention is just to say last line we are writing, that is mature and commercial this, but need Indianization in membrane development, and we had some success on this membrane development. at BRC. This is a typical membrane configuration or MEA configuration. First is this is the membrane central portion. There in the both side there is a catalytic layer for this degradation of this breaking of water into hydrogen and oxygen, and there is one this gas diffusion layer at the side. And with this thing, this is the MEA assembly which is developed here using our own membrane as well as an Nafion membrane also. Whatever testing it has been done, what we can achieve is that we can see the performance of our this is the green one is the Nafion based MEA, and red one is our own MEA, that is SPP, silicon oxide nanoparticle. So we can see performance, they are almost matching, or they are in fact matching. Only here there is some deviation, otherwise performance wise they are at par. And this is for open circuit voltage. If you measure, we can see there is no variation with number of cycles. So it is very stable performance we have achieved. Almost 200 cycles have been operated. Now that is done in that experiment was done in fuel cell mode, but actually our intention is the electrolyzer mode. So if you make a electrolyzer, it will be look like this. And next target is, so far in electrolyzer mode, we have achieved up to 4 liter per hour, normal liter per hour hydrogen production. Our target is something 80 liter per hour. And if we see the performance, we can see hydrogen production rate at different power consumption level. So it is quite matching, and it is our intention is to further improve in this performance. In a nutshell, whatever in the closer we can say, this speak membrane with PEG and silicon dioxide nanoparticle. This is the membrane. Then MEA assembly is prepared, and that is tested in electrolyzer as well as fuel cell mode. And if you compare with Nafion membrane with our speak membrane, we can see their performance wise they are matching, just matching. There's little bit difference in this ion exchange capability, but does not matter. We can see the conductivity, they are at par, at same. The next is high temperature electrolysis. We all know that at the temperature, the total this power requirement or energy requirement for electrolysis is less. And another advantage is some energy can be given as a heat only. So total electrical energy requirement, which is very high quality energy, is less. So naturally, one thing is this energy efficiency. We can say it is 50 to 55% energy efficiency is possible. For alkaline, it is around 30%. And at the same time, high quality energy requirement is further reduced. So it is more economic. So what is the development stage? That material development, what is done at BRC, that is the electrolyte development, which is 8% yttrium stabilized zirconia. That material is developed as an electrolyte, and as an anode material, strontium doped lanthanum magnetite. So that is also developed, and I'll show in the next slide. It is how it will look like. And nickel yttrium stabilized zirconia ceramic as a cathode material. So the steps of production of this high temperature steam electrolyzer tubes, that is nickel oxide and OSZ cathode, are first prepared by cold isotopic pressing. Then it is deep coated to make the electrolyte layer. Then again LSM layer is as a anode is again coated by deep coating method. Then finally it is co-fired to make the final this cell module. Then it has to be made in a cell form for this electrical connection, etc. What is we have achieved so far? We have achieved up to 50 square centimeter this area, this STS, high temperature steam electrolysis cells, and it has operated up to 72 hours at 850 degrees centigrade temperature for single cell, of course, single model. This is the test setup. It has shown quite good performance. Now next target is in a multi-cell configuration where 2 into 2 cells, 4 cells of the same size will be prepared, and it will be used for this hydrogen production demonstration as a STS mode. In the nutshell, whatever BRC has done so far is the basically alkaline water electrolysis development. We have developed an industrial scale alkaline water electrolyzer which can produce up to 10 nm³ per hour. And we are next plan is target is to increase this production per unit capacity to 30 nm³ per hour. At the same time, lab scale electrolyzer also developed at 4 NLPH per hour capacity. Then PEM electrolyzer, we have so far demonstrated up to 4 NLPH per hour hydrogen generation capacity, and using our own MEA. Okay, the next is high temperature steam electrolysis. So far demonstrated is 1.55 NLPH. Of course, if 4 cell, it will be something around 6 NLPH. That is the target. And this is the techno-commercial evaluation of the typical electrolytic hydrogen production plant, including the power source, that is green electricity or green energy sources. That model has been developed. That is also available with BRC. So if you see the industry, whatever today is available, most of them are selling this electrolyzer with a alkaline water electrolysis process. Few are even going for this PEM based method. And out of this, the last one, Eastern Electrolyzer, they have taken the technology from CSIS, CCRA, and up to 0.5 NMQ per hour is a PEM based electrolyzer. Their electrolyzer cell, all the other electrolyzer cells, whatever capacity may be, up to 600 normal meter capacity is available, they are made from imported electrolyzer. But this one is indigenous developed electrolyzer, but still they are also used Nafion membrane. Membrane is still imported. If you see the worldwide, what is the typical this worldwide green hydrogen production project, which is already completed or nearly completed? That is Asahi Kasei, Japan. That is earlier it was having the maximum size, that is 10 megawatt single cell stack. They are operating for I think from 2014 or so. Next, recently this was completed last year only. That is at Canada. This is liquid air they have produced. This PEM based electrolyzer, they have gone for 20 megawatt. Each cell is 5 megawatt cell. So that is commissioned recently as a green hydrogen project. And this is going to be the next bigger step. This is almost final stages of this commissioning. That is 88 megawatt PEM electrolyzer plant, which is going to be the biggest in this category at present. So as a economic analysis, if we see, so what we want to say here, for a alkaline water electrolysis, whatever we are at this condition, this is just a comparison. This is showing how with the increase in scale, how production cost will decrease. This is just a schematic. It is levelized cost of hydrogen, and this is the basic parameter assumed for that to getting this kind of model. What our target is, as of today, USDOE target is $4 to $5 per kg. That's the cost of hydrogen. So our technology, if we go for this levelized cost for electrolytic hydrogen production with optimal pressure and technology, we can go up to $4.45 per kg hydrogen we can reach. And there we can see the operating cost is 37%, 46% will be the capital cost, and rest are simply compressor cost to get the particular pressure. So if we go for a commercial level plant, these plants are quite small. So what we have to go for, cost of green hydrogen production in India, this is a commercial level based on today's technology, or some scale up is required. What we can see, the cost of green hydrogen, so almost 55% cost is the power production cost, that is from solar power cost, where the most of the cost goes to solar panel, and rest of the cost is installation of that panel, including its inverter, etc. That is also quite expensive as on today. What I want to say, for 1 megawatt electrolyzer plant, we have to go for at least 5 megawatt solar plant, based on, because solar plants are demonstrated always told as a based on the peak capacity. So actually for average capacity of 1 megawatt, we need to go for higher capacity. And as this there is a fluctuation in production, we have to go have a battery energy storage system. That will also add to the cost. So overall cost will be something 55% will be the cost of this energy production. Around 45% cost will be the electrolyzer generation plant. Out of that, there is of course the total OPEX, CAPEX both. And if we go for PEM type of electrolyzer cost will be around 25% more compared to alkaline water electrolyzer, as per whatever today's condition is. Then of course the balance of the plant cost will be little bit less compared to alkaline water, but module cost will be much higher compared to alkaline water electrolyzer plant. So in the short, we can say if this kind of technology is there, we can reach something $4.5 to $5 per kg of hydrogen as per today's technology for this kind of capacity plant, that is 1 megawatt electrolyzer plant, which will produce almost 425 kg per day of hydrogen, which is equivalent to 200 normal meter cube hydrogen per hour production. And how we are doing nowadays, people are using modular electrolyzer. And if capacity has to be increased, simply this number has to be multiplied. Like this is one plant at Peru. They are using 3.5 megawatt each electrolyzer, 7 electrolyzer in series they have made to make around 25 megawatt.
I think now close fast.
Yes, sir, it is the last slide, sir. So whatever is being told, so it is just summarized here. So I can only want to tell these things that present cell module developed is near ambient pressure. So some more modification is required to make it a little bit higher pressure operation. Cell module and balance of the plant is many advantages and at par with the international established manufacturer. There is no inferiority at all in this. At least our cell module we can guarantee that. And the industrial participation is required for cost reduction. Right now, I think this cost is little bit in higher side. So if you want to reduce the cost, some industrial participation is required so that there is a industrial production line is there. Otherwise, single production, individual one or two module if it's to produce, their cost is going high. And another for PM and R&D on high temperature steam electrolysis already is being talked. And we like to acknowledge that whatever inputs we got from PMD Vashi, Metallurgical Group, DMTD and CHED for PM development and our original equipment manufacturer for fabrication of the system. And we got a lot of inputs from this publication, internet information from NMRL, DST, TERI, ARENA and USDOE, etc. Thank you. Thank you very much, sir.
Thank you, Bhanja. Good to know that alkaline water unit is already sort of a commercial unit has been developed and a good progress has been made for PEM and high temperature steam. And I think with this we can we'll take up questions for you at the end. Please stay on. We can go to the next speaker. Next speaker is Professor Ghosh from IIT Bombay. He is a professor in the Department of Energy Science and Engineering. He received his doctorate in mechanical engineering from RWT at Aachen, Germany. He's a recipient of Weizsäcker Fellowship from DST, Erasmus Mundus Fellowship from European Union, and has worked as a guest scientist in Forschungszentrum Zürich for about 2 years. He has also worked in National Chemical Laboratory, Pune. His research interests include low temperature fuel cells, which include designing, modeling, fabrication, and characterization of PEFC and high temperature PEFC stacks. And he's also involved in solar hydrogen research and energy storage. And he will speak on high platinum cost obstacle or blessing for commercialization of fuel cell technology. Please try to limit yourself to about 50 minutes. Professor Ghosh, please.
Yeah. Good afternoon, everybody. Dr. Grover, thank you very much for the introduction. Yes, I'll try to keep it in within 15 minutes. Would you? Okay, I wanted to share my slides. Is it visible? Can you hear me?
Yes, please go ahead.
Okay, thank you very much. So initially, I thought that I'll be talking on that particular topic of Dr. Grover mentioned, but then after that, I realized that it's not only that one, it's also that out of the developments we are doing in IIT Bombay, I should also mention that. And then probably I designed my presentation around also like general introduction about PEM fuel cell and other thing. But while discussing and also while hearing the other speaker, I was also trying to rearrange my slides. So there will be probably some hodgepodge so that I could remove some of the things. Only one thing I want to discuss that why hydrogen is very important when you discuss in the context of the diesel or fossil fuel. And I'm going to discuss mainly on the transport sector because that's what I'm working the development for PEM fuel cell. So if you take the diesel and if you take the total 400 kilowatt hour total energy, chemical energy, and if you take the weight and volume, you can see here how it looks like. If you talk about that gray color, that is the total weight and total volume, and the other one is that the fuel weight and fuel volume. And if you compare to that, because that commonly this is very popular discussion that it will be electric vehicle with the battery. And if you see the total 100 kilowatt hour same system, if we talk about that, you can see the total weight and volume, how it looks like. And you can see that there is a huge variation in the weight and as well as volume. And for that, there is an alternative in between. If you can find that hydrogen actually can be placed in between these two, where you can get, if you take a state of art, let's say 6 kg hydrogen, if you are storing at 700 bar, then probably you will be requiring around 125 kg of the total system weight. Out of that, 6 kg will be the hydrogen volume and also the weight. So this is in between. So that's what probably you can see that with this amount of hydrogen, I will be seeing in the next slide that how far you can go. So that's the next important aspects where actually you can take care with the hydrogen is that the refueling comparison. If you take the present system where you are using diesel, and if you actually refuel for 1 minute, you can travel 800 kilometers if you take this type of system. This is being taken from a German website. And then if you take the now battery system, then you can see that if you take a supercharger of 120 kilowatt, and if you actually charge for 1 minute, you can travel 8 kilometers. So this is one of the major disadvantage. If you see that if you are traveling from one place to other place, you cannot sit for 1.5 hours to charge your battery. And this is also, if you sit 120 kilowatt only for one car to be actually charged at a time. So it's in series. So if there are 10 cars, actually it's an almost 10 hours affairs. Okay. So if you take a hydrogen based system in that sense, and if you take similar kinds of, let's say, filling station in kilowatt, that's a 1 kg of hydrogen per minute if you can refuel. So, and in 1 minute, you can actually fill 100 and then you can drive 100 kilometers. So you can see that between the diesel and electric car, there is also hydrogen as a carrier, which plays a very important role, and it can be actually useful. So in this context, hydrogen comes into picture, and then one of the components where hydrogen can be used is the fuel cell, and in case of transport sector, it's the polymer electrolyte fuel cell. And I'm just keeping these few slides very fast because this is known. So as I'm going to discuss about polymer electrolyte fuel cell, so in this case, hydrogen is used actually as a fuel here, mostly pure hydrogen, because platinum is being used as a catalyst here, and then hydrogen is getting oxidized on the anode side, and you have a membrane. It's a Nafion membrane, which previous speaker was also talking about. And then H plus ion goes from this anode side to cathode side. Electron comes to the external circuit, and it actually reacts here with oxygen, and then finally we get an water as a byproduct. So now if you see the different components in the PEM fuel cell, so it is the electrolyte, then it comes the electrode, then supporting layer. You can see these are the being shown here. This is the electrolyte and this is the electrode. Then this is a supporting layer, or sometimes we call it as a gas diffusion layer. Then the bipolar plate and sealant or gasket and the end plate. This is how it looks like. And if we go for the now different components and challenges, then if we just combine these particular components in different sector, like this, a membrane and electrode is one of the group of the components. Other one is gasket, gas diffusion layer, bipolar plate, and end plate. And there is also some design factor, like how you are designing the entire system. And if you see the responsible for these types of components are actually responsible for, let's say, for the membrane and electrode, mainly responsible for the cost and durability. If we talk about the design factor also, to some extent, it's also influenced the durability of the system. And if you go for the transport sector, because then weight and volume also comes to a picture, because you have to make a very light system, as well as volumes. It should not be also it should not have high volume. So that's also coming mainly from the bipolar plate and end plate. So actually we are working in IIT Bombay in all these aspects, because we are mainly working on the transport sector. And so now if you see the target, so some of the things, as we have talked about the cost and other things. So one is the lifetime. So earlier, if you see that ultimate target, it should be 8,000 operating hours, but now we have a target of let's say 4,000 and 5,000 in different years. Cost wise, you can see that the target cost is given to $30 per kilowatt, which is really very tough and steep target. And some of the specific power you can see in terms of gravimetric specific, gravimetric power density and the efficiency. And other one is that if you talk about the energy storage that I'm skipping at this point of time. Now I want to discuss only the membrane. As we are earlier, we have seen the total system cost. What we have talked about is only $30 per kilowatt. Now, if you go for the conventional, if you go for the Nafion membrane, and if you take the cost of Nafion membrane at a particular rate, and then if you see that the total area you need of the membrane for 1 kilowatt system, then you can come out with this number $40 only for the membrane. Then the catalyst is the other one, where if you take the similar kinds of calculation, you can find that per kilowatt you need $60 only for the catalyst. So itself membrane and catalyst contributes to the $100 as at present if you take this. And then that's the reason people talk that platinum is the culprit, because of the platinum is very expensive and it's not coming in the market. But I actually have a different opinion about this. Because this catalyst or platinum, what we talk about, as it is a catalyst, at the end of the lifetime of the fuel cell, almost 90% of the catalyst is available. So if this catalyst is being recycled, then we should not consider 100%, we should consider only 10% of the cost. So which is actually equal to $6, not the $60. So this is something that what I generally discuss, and I'll be coming to this particular point afterwards. So then other one is the bipolar plate. So bipolar plate, at present people use graphite bipolar plate in most of the cases, and you have to machine it, or in some way, if you get, this is one particular bipolar plate itself costs around $140, which can give you around 300 square centimeter and equivalent to some amount of watt. And if you convert into kilowatt, so we need around $1,000 per kilowatt only for the graphite plate. And this is for not for a mass production, of course. This is for an individual prototype. These costs can be brought down, whether bipolar plate cost or Nafion membrane cost, but not for the, of course, the platinum cost. As you know, this is the precious metal catalyst, so you cannot bring down the cost by mass production. Probably that cost will go up. And the alternative material for bipolar plate, what we are also trying to do, and that is very important, is that metallic bipolar plate, which can be done, because here you can see that is this graphite plate is being machined mostly. So in that case, it's become very expensive. But in this case, you can do hydroforming, and that cost could be at as less as $2 to $3. And we are also trying to make this type of metallic bipolar plate. I'll share some of the things with you in few slides. These are some of the other people who have done from my earlier lab, as it was mentioned, frozen center English. So now in this context, there the thematic area that what we can work in terms of fuel cell is that one is a fuel cell stack. Other one is that hydrogen storage system, that mostly that 700 bar compressed hydrogen storage that can be also worked on. And balance of plant is also very important. And I wanted to mention, because we are struggling now, because we have the fuel cell stack at least ready for 5 kilowatt. But we need to test it, and we need to have, and we are always trying not with oxygen, always we are trying with air. So we need to have an air blower. And to buy this air blower, even it's very difficult. We are not getting in India to buy that air blower. So this is also, even designing the balance of plant is also very important. And finally, the system integration is the next component. So at IIT Bombay, if you take that, we started with first small cell. If you see that this is the scaling off of the cell, we started with 25 square centimeter few years back when I joined here, and then slowly now it's a 300 square centimeter. We have actually gone to 400 centimeter square now with a metallic bipolar plate. And always I want to mention here, always we are trying to actually test with air, mostly with air. Here you can see oxygen, but always we do without humidification. So we do our own humidification inside the cell itself. So we do not use any external humidifier for this type of testing. And then we have different types of design and different types of operating system. And we have got a total power, if you see the total current density and power density, and these are all at 0.6 volt. We have got this, this is the total power we have got per cell. This is the per cell what we have got till now. And we have the, after that we started that large scale development what we are trying to do. So we have our own coating machine here where we try to make our own CCM. This is carbon catalyst coated membrane. Here you can see. And then we try to assemble the MEA, and then finally this is our own flow design, and then try to test the fuel cell stack. It's a single cell testing, what you can see here. And also we have our own current density mapping, because when you are scaling up, you will be having a distribution problem of the gases and reactants. As a result of that, you will be having problem in the performances. So we have done some this is also we have patented in our in IIT, and this we use for current density mapping. So we know that in scale up how the behavior is actually how it's changed. Then after that we went for, this is a graphite based, till this point we were in the graphite based system where we tried to make 400 centimeters square active area fuel cell. And this is around 10 cell stack. You can see 1 kilowatt stack. And we can also tell here that one of the major challenges which is always being overlooked is the gasket. And so we have our own gasket. Even we design our own gasket so that we can make directly. You can see here that we are trying to dispense the gasket for our customized design. And then this is a 1 kilowatt stack, and then you can see that we directly use a small air compressor and try to put it here and then see the performance with this. And this is the performance what you can see, and this is a small video what you can see here. So we have already tested with 1 kilowatt fuel cell. Now we are going for 5 kilowatt stack, and so that is underway. And in between we are also trying to, because we are planning to make this 5 kilowatt stack for a vehicle, but ultimately we had some problem with the funding, so we had to go with a smaller version of that. So this is a 600 watt fuel cell stack we developed for a scooter. So this you can see that how we are just making it, and all the components we actually do was designed by us, and then we made it. And this is around more than 600 watt we could achieve with this. This is total 19 cell stack. And finally, using this stack, we try to make a scooter. This is a scooter. So this is an off-the-shelf. We bought an e-scooter, and then we actually retrofitted in it. Initially, this was the first version where we are putting the cylinder, hydrogen cylinder. After that, we made a nice looking scooter. Here you can see there are 2 hydrogen cylinders that they are connected. And then the stack, because we didn't have any space here, so we had to actually mount the stack in the front of this. And we have tested few times till now. So that is the status with our 600 watt scooter run with hydrogen. So after this, then we started going with the next version where we wanted to have a 20 kilowatt stack developed. And this is we wanted to actually put in a Tata Magic vehicle. And this is in collaboration, of course, with Tata Motors, this one as well as the previous one. So we are in the process of this, still it's not done. So in this process, we have actually made the metallic bipolar plate. You can see these are the metallic bipolar plate what we have. This is our 220 centimeter square area metallic plate, and this is still this is not the final version. Still, we have to do some of the work on that. And this is the 400 centimeter square area flow battery. And then finally, we have also done that gasket. You can see that we have dispensed our own gasket. So this was one of the major challenge for us when we are going for scaling up. So now that bottleneck is actually we have overcome. And this is the balance of plant. We have air subsystem, hydrogen subsystem. This air subsystem, as I was telling, that we are struggling with the air compressor because we need very compact air compressor for the vehicle. And so we have taken a target that this is the performance, or this is the characteristics for Toyota Mirai vehicle Honda Clarity. This is our vehicle, our stack what we are planning. It will be 1.5 kilowatt per liter. We are far away from them, but still, if we can achieve this one, it will be good achievement for us. That's what we feel. And this will be requiring from now another 1.5 year time. We are actually aiming for this particular thing. Other than that, these are the main actually work what we have done. But in the research level, as we are in R&D lab, so for our PhD student, we are also working on ABPBI membrane, high temperature PEM fuel cell. So this is being done already. And then this particular membrane, we are not only restricting to the fuel cell activities. We are also using it for flow batteries, and it's also showing very good. And as well as for the electrolyzer. These are some of the just photographs and then some of the results you can see here. I'm just hurrying off because almost 15 minutes is over for me now, it looks like. So next one is that we are also working on unitized regenerative fuel cell, where we can use the fuel cell as well as electrolyzer in the same system. And we have tested this. there are some challenges with this, and this is PEM based, not alkaline. So PEM based, there was some problem with the carbon corrosion, and then catalyst was getting washed away. So after a few cycles, actually the performance was going down. So, and the other part, what I want to tell, I just will take another 1 minute of time. So as I was telling platinum recovery thing, just I want to tell you in very short that if you take this particular thing, that platinum can be recovered after the end of the life of the fuel cell. And this is a country like us where we believe in putting, investing money in gold and putting in the locker. So, and if you can get it back out of the locker, so then there is no problem. People love doing that. So in that case also, if in a fuel cell, if we are actually investing in platinum, and if we can get 90% of that, and you can see that it will be really beneficial taking this. So this is some analysis I have done. I don't want to go in more detail of that. I want to just show you, this is, I have taken two scenarios, because people always say that we should reduce the loading. I have told that one scenario is that you have more loading, other cases you have less loading. You can see in terms of platinum, you are saying $32 per kilowatt, others says $3 per kilowatt. That's a target for let's say DOE target. And if you take this, and then after that, if you do all this analysis, like you can see, this is the platinum cost, how it changes with time. If you have taken from this is an historical cost of the platinum, if you see this, and you can see that in 5 years, this was the rate at which it has increased that cost. This is the 10 years, and this is the 15 years at which. And if you do these calculations, you'll be finding that I'm just going to one particular point, that you will be getting that the platinum salvage value will be more than the total cost what you have, and net present value will be around 41. This is for your fuel cell, you are paying $41 per kilowatt, and your platinum salvage value is $61 per kilowatt. So that means you can make a business out of it if there is actually a business model is available. So this can be done for different scenario, and I have done all of them. This has been published, so only want to touch upon, as I told in the beginning, that platinum is not at all culprit. If there is a proper business model available, then probably this particular business, platinum can actually promote this fuel cell business. So it is like this, that you are using a platinum in a fuel cell, and it's something like this, that you can use it for your daily purpose, like in a car, like you have a horse, and this fuel cell car is like a horse, I compare always. So you are using this for your daily purpose. And at the end also, if sometimes you find that there is a racing is going on, so you can also, for betting and for this thing, you can use this your own horse and also go for betting. The same thing also happens, that in you can get at the end also the platinum back, and you can do some types of this type of analysis. So this is what I wanted to conclude, that fuel cell is an electrochemical device, and I will not be just reading off all these things, but I want to tell that we have gone to a level of fuel cell stack development, and probably in another 1 or 2 years time we'll be in a position to demonstrate in a vehicle. Thank you all for your attention, and if you have any question, definitely at the end I'll answer.
Thank you, Professor Ghosh. I'm happy that both Professor Ghosh and earlier Kalyan Bhanja they have tried to benchmark whatever they are doing with whatever is available from international companies. They both are good developments. Now we move to the next speaker, who is again from BARC. Can I have the biodata? Yes. Dr. Shriniwas Rao, who joined BARC in 1988 after completing BTech from LIT Nagpur. And he has been working in the development of processes related to the front end of the nuclear fuel cycle. He received his PhD from HBNI for his work on Bunsen Reactor, which is the key process, a step in iodine sulfur process. And he's presently leading a team working on the development of thermochemical processes for production of hydrogen. And he's heading the material development section in Chemical Technology Division. And he is going to speak on the development work carried out for hydrogen production from thermochemical cycles, particularly iodine sulfur process, which is expected to have higher efficiency. Dr. Shriniwas Rao, please.
Good afternoon, sir. I'm Shriniwas Rao. Thank you for the opportunity given by INAE Mumbai chapter So I'll be mainly talking on this iodine sulfur thermochemical process. We have heard electrolysis and then fuel cell now. So little bit of change of this production method. So this iodine sulfur process, as such, 3 reactions are there. This is the basic reaction: iodine, sulfur dioxide, and water, giving hydrochloric acid and sulfuric acid, which are further separated, and then HI is broken into hydrogen and iodine at 450 degrees centigrade by using catalyst to get hydrogen here, and iodine goes back. Similarly, sulfuric acid, the final SO3 decomposition takes place at 900 degrees centigrade to get SO2 and oxygen comes out here. So what we can see is water is the input, oxygen and heat is oxygen and hydrogen are the outputs, and heat is the input here. So all other chemicals are recycled. That means consumption of chemicals is as such negligible. So the areas of concern here are corrosive chemicals like all iodine, HI, sulfuric acid, SO2, and temperatures are more, 900 degrees centigrade and 450 degrees centigrade, and we require catalyst for this SO3 decomposition also. Then comes metal of construction because they are corrosive chemicals, then recycling of chemicals, and finally closing the loop. That means not wasting the chemicals as such. So generally what we see in literature, it is SI process, they call sulfur iodine. BRC has been using this terminology of iodine sulfur process. The advantages being it can be coupled to high temperature nuclear reactor or solar concentrators, and it has high efficiency of around 50%. So it is a closed loop process, as I just told now, all chemicals are recycled. And it is a all fluid process. That means only gas and liquids are used in the entire process. So working becomes relatively simple. Then it is a promising method as it is efficient, greenhouse gas emission free, and capable to have large scale hydrogen production. These are the different activities going on in BRC. With electrical heating, glass closed loop has been shown, closed loop in glass setup has been shown. Then metallic Bunsen section, that means these are, we have graduated from glass to metallic systems, hydrochloric acid and sulfuric acid sections, and now we are working on closing the loop in metallic system. Also, this molten salt heated, same IS process with 150 NLPH capacities planned to just improve the thermal efficiency of the process as such. And then for data generation and developmental activities, various things are going on as this technology is getting matured. So in glass setup, we have studied all 3 sections, that is Bunsen, hydrochloric acid and sulfuric acid section at atmospheric pressure condition. All chemicals were recycled, and we got hydrogen and oxygen by giving only water and heat as the input. And we could produce hydrogen at 30 normal liter per hour. So the feasibility has been established, and after USA, Japan, China, and South Korea, India is the 5th country to show this glass closed loop operation for IS process. So these are the few pictures, whatever we have done in the boxed up condition. This is first floor, this is second floor here. So all the equipments were put inside as iodine, SO2, and high temperature also is there for safety purposes. This is the Bunsen reactor where water is getting split, and we get like this light phase sulfuric acid and heavy phase HIX, that means HI and additional iodine, HI plus iodine. So these are the other equipments. Similarly, in HI section, hydrotic section, this is the distillation column where iodine has to be separated, which goes back to the Bunsen reactor. And this is a distillate HI, which goes further for decomposition. Coming to sulfuric acid section, we have in quartz, we have decomposed sulfuric acid at around 900 degrees centigrade, and then the gases are cooled and further processed here. Then to move on from glass or quartz to metallic system, there are many equipments having different temperature ranges, right from 900 to 127 or 120 centigrade, having different compositions of chemicals. It is either vaporization or boiling, and then we have distillation column, sulfuric acid decomposition at 450 centigrade, or SO3 decomposition at 900 centigrade. So we have done corrosion test studies for quite a few materials like tantalum, hastala, incoli, silicon carbide, and noble metals also, and we could identify various materials for these various equipments operating at different temperature ranges. So to start with, we have studied this Bunsen reaction at high pressure. So we had built the plant. It is like an industrial plant having all the features of a typical chemical plant with all safety, interlocks, alarms. So SCADA PLC system is there. Then we had spare pumps also in the system. In Bunsen section, we got this operating range 60 to 80 degrees centigrade, pressure from 2 to 6 bar we had studied, and then we could get a very good product at around 6 bar pressure at 70 degrees centigrade. We can see here the atmospheric pressure, two phases were something different, and that high pressure things, these two phases are far better, in the sense they are more purer. Similarly, we have worked on sulfuric acid system. This is a Binotube reactor made of silicon carbide. This is the internal tube here. The catalyst is on the top portion. In the bottom portion, we are vaporizing sulfuric acid. In the middle, sulfuric acid is decomposed to SO3, and here, in the presence of catalyst, SO3 gets decomposed to SO2 and O2, which comes out from this inner tube. So this foam type catalyst, chromium doped iron oxide catalyst, was developed at BRC, and then it has been given good shape to get a high surface area. And this is the typical arrangement what we had tested. Similarly, HI decomposition is a equilibrium controlled reaction. So 22% is the equilibrium composition at 450 degrees centigrade. So if we are able to remove one of the products, either hydrogen or iodine, then we can increase the one-pass conversion. So within BRC, this membrane, metallic membrane tubes have been developed, tested for their hydrogen permeability and all those things. And then system was made of single tube reactor, and also some 4 tubes membrane reactor also was made and tested. And we achieved one pass conversion as high as 80%. That means instead of 22%, we can get 80% conversion in single pass. So that reduces a lot of heat load, and then energy efficiency is improved. We can reach the thermodynamic efficiency. Similarly, this, as I just told, chromium doped iron catalyst was developed within BRC, and then it has been given shape by this ceramic shaping techniques. These are the steps here. Template foam was impregnated with ceramic slurry, and then whatever catalyst was made, we tested for its performance up to 100 hours, and it showed a stable performance in lab scale, also on the larger batch of the reactor, what I showed just few slides before. So that also was found to be stable with time. Then coming to HI decomposition, this is platinum loaded gamma alumina catalyst which is developed. The process is almost somewhat similar to that earlier sulfuric acid catalyst. And the catalyst showed uniformity in structure, and the performance what we got was 90% of the equilibrium yield. Equilibrium yield is 22%, so we got around 20%. So this catalyst, both catalysts have been developed within BRC only. So once we have got the material catalyst, now we are going ahead with iodine sulfur metallic closed loop, which will be heated electrically, and then deliverables are operating experience of closed loop facility with recycling of chemicals, then measurement and control technique standardization, and naturally engineering steel materials of under continuous operation. So this is the layout, and this is the actual work going on now. So within 6 to 8 months, we'll start commissioning the metallic closed loop of 150 liter per hour hydrogen. Similarly, we are working on the solar hydrogen demonstration facility, again of same capacity. Here directly solar energy will be used. So to improve the energy efficiency of the process, demonstration of solar energy utilization for hydrogen energy generation. So deliverables will be harnessing solar energy at high temperature using heliostats or parabolic tubs, distributing the heat to the process IS plant as such, and thermal storage of solar period. It's either molten salt or phase change materials. And finally, the objective is to have the closed loop operation of IS plant. This is the scheme, overall scheme for solar heating process of IS process. The temperatures for up to say 200 degrees centigrade or 215 centigrade, parabolic tubs will be used. For up to 500 degrees centigrade, central receivers, concentrators will be used along with intermediate LBE or molten salt. Those things are there in place. Then for the only high temperature requirement of 900 degrees centigrade, what everybody tells that it is very high temperature process, etc. It is only SO3 decomposition which requires 900 degrees centigrade temperature. Otherwise, it is all 450 degrees centigrade or so, or maximum, let us say 500 degrees centigrade. So this, in this particular case, we are going to heat it by electrical heating. Then quite a few challenges we had overcome. Basic process chemistry has been understood. Feasibility has been established. Then for sulfuric acid, we have non-noble metal catalyst based catalyst has been developed, that is chromium doped iron oxide catalyst. Then high developed efficient catalyst for HI decomposition also. Then membranes, this is also very good development at BRC, which improves the thermal efficiency of the process. Then materials have been identified and tested. Then this indigenously developed silicon carbide reactor for decomposition of sulfuric acid. Indian vendors only have developed these components which operate at which can see as high as 10 bar pressure, and they are non-porous. In process integration in sulfuric acid decomposer, we could achieve by vaporization, decomposition of sulfuric acid and decomposition of SO3, including heat recuperation in the same system we could get it. So some analytical techniques we have developed, sampling techniques for process chemicals because temperatures and chemicals are at pressure and high temperature. Then identify instruments for high temperatures. So still the things to be done for further improvements are reduction in amount of iodine recycle by developing electrochemical Bunsen reactor where iodine requirement comes down drastically. Otherwise, in regular chemical process, it is iodine which is separating hydrochloric acid and sulfuric acid. Then for further process integration, reaction cum separation in countercurrent agitated Bunsen reactor, which we will be doing in metallic closed loop as we have seen just before. Then catalyst for HI decomposition, we want to replace platinum. That job also is going on in BRC. Then development of online composition analyzers, then coupling to primary energy sources like either solar or nuclear, that studies have been taken up. So prolonged testing of material, anyway, it has to be done in metallic closed loop. Then identification of limiting process equipments for scale up, that is also going on. And not last but the least, and development of vendors, which will play a major role for critical components like silicon carbide and other things. Coming to global status of IS process, Japan, China, Korea, and USA, they have been working, we know that. So Japan is aiming by 2025, 30 normal meter cube per hour of hydrogen capacity plant using engineering materials with helium and electric, these things. Similarly, China talks of with engineering materials, this STR-10 hydrogen plant, again by 25. And South Korea is working on 1 normal meter cube per hour engineering plant of hydrogen using engineering materials, helium and electric as the heat supply. And IIT Delhi and ONGC have been working on this IS process for this sulfuric acid section, catalyst development, and some Bunsen section studies also using electrical heat naturally. So with this I end. Dhanyawad.
Thank you, Dr. Shriniwas Rao, for taking us through iodine sulfur process. I think it can be much more efficient than electrolyzers if developed fully, or rather when developed fully. So with this, we are also sticking to time, 15 minutes. Now let's go to the next speaker. And we have the, yes, it's Dr. V. Sudarshan from BARC. He works in the chemistry division of BARC, and he received his PhD from Mumbai University in 2002 for his work on structural aspects of inorganic gases. Subsequently worked for a period of 2 years at University of Victoria, British Columbia, Canada, the area of structural aspects and luminescence properties of inorganic nanoparticles. And currently he is working on hydrogen storage materials, gases, luminescent nanoparticles, etc. And he is a recipient of Science and Technology Excellence Award in the year 2010. And he's going to cover various aspects of hydrogen storage in intermetallic alloys. Dr. Sudarshan, please.
Am I audible now? Am I audible now? Yes. Shall I continue? Okay. Thank you very much, sir, for the nice words and nice introduction. So I thank INAE Mumbai chapter and senior colleagues from BARC for giving me an opportunity to talk in this forum. So I am going to talk about metal hydrates as candidates for hydrogen storage technology. I am from chemistry division, BARC. So the metal hydrates, as already the concept has been already introduced by Professor Ghosh, the metal hydrates are ideal candidates for storing hydrogen. So we will discuss in this presentation. So plan of the presentation is like this: why solid state hydrogen storage? Maybe one slide I will show. And DOE targets and what are the focused areas in Bhabha Atomic Research Center, and the results on some promising systems or promising technologies which have been developed in BARC. And then I will end with cost considerations. So for comparison, why hydrogen storage is important, we have to compare with the volumetric energy density as mentioned by Professor Ghosh. The volumetric density of hydrogen gas is very, very low. You can see it is around 0.898 gram, 0.089 gram per liter. And density of hydrogen liquid is better, but liquefying hydrogen gas takes a lot of time and a lot of energy, and it's an energy intensive process, a lot of money is involved in that. But if you consider the density of gasoline, it is quite high, if you can say, depending upon the compressibility, etc. We can range value from 710 to 770 gram per liter. And we all know for a fuel cell based vehicle, the onboard hydrogen storage requirement is around 5 kilogram to 13 kilogram to run a kilometer or run around 500 kilometers. So efficient hydrogen storage is need of the hour to make hydrogen based applications or hydrogen based technology in transport sector. So as mentioned by Professor Ghosh, the metal hydrides are very efficient. They have got very good volume density. Metal hydrides are promising candidates for hydrogen storage. As you can see from this graph, the green color plot, you can see it absorbs around actually 120 grams of hydrogen per liter. You can see. So compared to all other technologies, the metal hydrides are quite promising for any transport-based application or in the transport sector based on hydrogen technology. So any hydrogen storage technology, we should always relate to the what are the targets set by Department of Energy USA, because Department of Energy USA has set certain targets for 2020, 2025, and as well as the ultimate targets. So our material also should have a number which is close to the number given by this DOE, Department of Energy, United States. For example, gravimetric capacity, one should have, if you want to use it for transport application for light duty vehicles, then we should have around 4.58%. By 2025, it should be 5.5, and ultimate is around, I think, around 6.58%. Similarly, volumetric capacity also in this range, 0.03, 0.04, and 0.05, the ultimate level. So cost is also very important because cost comes from the material cost as well as the cost of the vessel. So if you compare that, if you consider both into consideration as well as the hydrogen generation technology, so it should be in the range of around 300 by 2025, $300 per kilogram of H2, and 266 by the ultimate goal. So fuel cost, which is always expressed in terms of the GGE, should be around $4. So what are the areas which are focused in BARC? The BARC colleagues are involved in the material identification for intended use. What are the different types of material which can be used? And then vessel design, fabrication, testing of solid state hydrogen storage system, modeling, simulations of hydrogen storage system to make it more optimum as well as more effective, and then the cost comparison. We call it the techno-commercial criteria to choose which system to use it in a particular technological application. So briefly, I show here what are the systems. Variety of systems have been investigated by colleagues in BARC. Like most of these are from transition metal-based system, titanium, chromium, vanadium alloys, vanadium, titanium, Fe alloys, zirconium, Fe alloys, variety of transition metal systems. Along with the uranium also people have studied, then carbon nanotubes, carbon, porous carbons, etc. There are two groups in BARC who works on this hydrogen storage technology. So these groups, based on these works, two technologies have been are found to be promising. One technology is based on titanium, chromium, vanadium alloy, as I mentioned here. Titanium, chromium, vanadium alloy is a ternary alloy made from transition metal. And another is a magnesium-based system, which is a nanocrystalline magnesium-based system that also shows very promising application. These two systems are found to be very promising. There are minor changes, of course. Any system will have both advantages and disadvantages. So these two systems also has advantages and disadvantages, but a time will tell. I think maybe another 1 year time will tell which system can be used for technological applications. Let us first discuss about the nano-engineered magnesium system, magnesium hydride system. This is first of all, how to prepare this nano-engineered system. We take magnesium hydride, which is commercially available, or we can make also from magnesium metal, and mix it with variety of transition metal oxides. And then we ball mill for several hours, maybe 12 to 15 hours in intermittent durations. Maybe 1 hour we will ball mill and then keep it for rest. And then this will repeat for several hours. And then we will do a dehydrogenation process. During this dehydrogenation process at 175 degrees centigrade, magnesium metal is formed and vanadium metal is also formed. So whatever this vanadium metal get dissolved at the surface of magnesium, and that vanadium acts as a catalyst for hydrogen absorption. Because pure magnesium, the thermodynamics is poor, kinetics is also poor. So if you use pure magnesium, we have to heat up to 300 degrees centigrade to absorb, around 250 degrees centigrade to absorb hydrogen. And if you want to desorb hydrogen, we have to heat at high temperature, around 350 degrees centigrade, because kinetics is poor. But by using a catalyst like vanadium, you can improve the kinetics. And in fact, the activation energy can be reduced to even half by using this vanadium as catalyst. And that way, they are able to reduce the parameters like desorption temperature, absorption temperature, etc. And the hydrogen storage capacity is also found to be quite high in the system, around 7%. So this graph you see here on the right-hand side top, I show a beaker containing water, ice, etc. And in that, there is a hydrogen storage device is dipped in there. Why it is like that? Because during hydrogenation, massive energy change, massive thermal changes are taking place. During hydrogenation, it's an exothermic process and lot of heat is generated. And during hydrogen removal or dehydrogenation, we need to heat the system. So any hydrogen storage technology also should take care of this concept of managing the thermal energy. In this case, there is a lot of thermal, even the temperature can go up to 200 degrees centigrade in the case of magnesium-based system. So people have calculated as activation energy, etc. from different experiments and found that by doping vanadium metal, we can get efficient absorption of hydrogen around 7%, and the dehydrogenation temperature also can be brought down to less than 200 degrees centigrade. Of course, these are some of the advantages, but there are some disadvantages, like nanocrystalline magnesium itself is highly sensitive. Because at the moment, the nanocrystalline materials are highly reactive, as you know, because a lot of surface area is provided. And also, when you make a dehydrogenation reaction, which in the previous reaction, there is a possibility of other vanadium oxides, which can detrimentally affect the kinetics and the hydrogen absorption capacity, as has been shown here. So this needs to be estimated, or this experiment needs to be carried out from large scale samples, like few kilograms, etc., before employing it for any technological applications. And also, you can see from here, within 40 seconds, this is also a good aspect. Within 40 seconds, we have getting almost around 7% hydrogen absorption. That means the kinetics is quite fast. That is also very much required for using this material for any hydrogen-based technology. So this is the technology developed, one of the technology developed. The another technology developed is based on a ternary transition metal alloy called titanium, chromium, vanadium. This titanium, chromium, vanadium forms an interesting alloy in this ratio, 2 titanium, 1 chromium and 1 vanadium. This alloy is bulk material only. This is prepared by arc melting. This is the typical arc melting furnace which we use for making this alloy. This is a typical button which we prepared based on arc melting. And this is around 5 to 6 gram of this pellet, or this button is having a weight of around 5 to 6 gram. And dimension, if you can see here, it is around 2.4 centimeter length and around 5 millimeter thickness. Hydrogen absorption capacity is somewhat low, means it is not up to 7 or 6.8%, it is around 4 weight percent or 3.8 percent. But it is quite stable actually. You can keep it in the ambient conditions also. The crushed alloy we are keeping in air only and taking the photographs. So we have also developed a methodology to make 300 grams of the alloy. You can see here the 300 grams of the alloy recently made in prepared at BARC. So this alloy particle can be put in a beaker. You can see this beaker is of 250 ml capacity, and its volume is around, we can see here, around 125 ml. This material which is occupying this 125 ml volume can absorb almost 144 liters of hydrogen. You can see from here. Actually, whatever the material which is kept inside a beaker can absorb 144 liters of hydrogen actually. So this is also one of the technology which is is found to be quite promising. This is made by arc melting method by starting from titanium, chromium, and vanadium alloy. This is some of this material. This can be put it in a reactor. The reactor has been fabricated in BARC, heavy water division. So this reactor has been fabricated. These are typical valves, and this can be connected directly to the hydrogen generation system, the alkaline water electrolysis based hydrogen generation system discussed by Professor Kalyan Bhanja. So this material can be put in this reactor and given hydrogen, and we can see how much hydrogen is absorbing, what is the capacity, what is the desorption temperature, etc. All those things can be made. This has been in-house developed for the study, detailed studies, and also cycling studies also can be done using this material. So what we do is we put the material in this and give different amounts of hydrogen and see how much, whether the pressure is building up or not. See, you can see here the pressure remains constant because whatever hydrogen we are giving is absorbed by the material. But a stage will come around 3.8 or 3.7. Thus, it becomes saturated. The material becomes saturated with the hydrogen and it no longer absorbs. Then whatever hydrogen is given, it increases the pressure. So by drawing a tangent, you can see how much is the capacity of this material, how much is the hydrogen storage capacity of this material, and it is found to be around 3.88%. So we have also studied a different experiment. We flow hydrogen because hydrogen is keep on coming from any reactor or any source or hydrogen source. It will be coming at different speed depending upon the production rate. So we have also done studies by different flow rates like 30, 45, 50 ml. There is no change in the hydrogen storage capacity and is remaining around 3.88%. Another important aspect of the hydrogen storage material is the desorption temperature. In our case, the desorption starts around 70 degrees centigrade and completes around 180 degrees centigrade. So of course, the reaction in desorption is almost completed at 180 degrees centigrade and it starts around 70 degrees centigrade or 80 degrees centigrade. And also, this in the previous slide I showed at very slow speeds of slow flow rate, means very small flow rates like 35, 40, 50 LML. And we have also done experiments at high flow rates like 5 liter per hour, 9 liter per hour, 18 liter per hour, and 34 liter per hour. And we found that if you go to higher flow rates like 34 liter per hour, there is a pressure buildup is seen. But at 5 liter per hour, reasonably good. There is not much pressure buildup is there. And the hydrogen storage capacity is also not decreasing too much. It is 3.7 is becoming around 3.18%. There is a slight reduction in the hydrogen storage capacity with this. And the same material only, we have also tried, or we have also estimated its hydrogen storage properties after keeping it for 1 year in hydrogen environments. So we did not see much changes in the hydrogen storage properties, and the material absorbed around 95% of its initial value, even after storing for 1 year. Some cost considerations also we have done. Some cost calculation also has been made. Our colleague Ruksha Bhattacharya has done some extensive studies on cost calculation using a software called HEAP, which is developed by IAEA. Using this program, he has also carried out extensive cost. She has carried out extensive cost involved in this hydrogen storage technology or hydrogen storage methodology. So the storage cost involves, as I mentioned, storage of the material and the cost of the material as well as the cost of the pressure vessels. So 2 types of pressure vessels you can use. Either you can use stainless steel pressure vessel, or you can use fiber reinforced plastics or fiber reinforced polymer. Of course, fiber reinforced cost is FRP, or the fiber reinforced polymer cost is 6 times higher than that of the SS stainless steel. And of course, density, the weight will significantly reduce. If you use the FRP as a container, the weight will significantly reduce. And the stress also will be significantly higher. It can withstand significant higher stress compared to stainless steel. And these are some of the calculations which you have done, not for our this Ta2CRV based material or magnesium based material alloys. It has been done for a commercially available material, hydrogen storage material LaNi5, which shows around 1.58% hydrogen storage capacity. In fact, we can see there is a reduction in the cost. You can see from here this table. When you use FRP cylinder as well as stainless steel cylinder, calculation has been done for 2 pressures, 150 bar as well as 350 bar. And you can see from here, when we use the hydrogen storage material along with the FRP, there's a cost reduction, significant cost reduction, as you can see from this table. So I thank you very much with this.
Thank you, Dr. Sudarshan. Well, I think it's very nice to see that we have been able to cover all the aspects of hydrogen production, storage, PEM fuel cell for usage. And now we move on to next speaker, Professor Yadav. Can I have his agenda, please? Well, I think it's very difficult to introduce Professor Yadav in a short span of 1 or 2 minutes, but since that's all the time we have, so I'll just introduce very briefly. He served as the founding Vice Chancellor of Institute of Chemical Technology, Mumbai. He was there for 10 and a half years, and currently he holds the titles of Emeritus Professor of Eminence and J.C. Bose National Fellow in ICT. He has several honorary doctorates and adjunct positions in universities abroad. He is a very productive researcher and member of several committees and councils, and also independent director of several companies and he was conferred Padma Shri by Government of India in 2016. ICT Mumbai is collaborating with ONGC Energy Center, and they are developing methods of production of hydrogen. Over to you, Professor Yadav.
Thank you. Thank you so much for inviting me for this very interesting, panel discussion. So what I have done that I have deliberately added some material because there are some people in the audience who are, policy makers, and also there are students. So they should know why hydrogen and what it can do. And so I'm going to talk about the potential of our technology developed as ICT OEC process. So this is well known, President US Joe Biden's Leaders Summit on Climate Change, where our Prime Minister also participated. And before that, in the Paris Agreement, where Shri Prakash was there, 195 nations had come. And so we know that our goal of the nations is to bring down the temperature of the globe below 2 degrees and preferably 1.5 degrees. And if you look at the CO2 concentrations in 2020, they were 410 ppm. This year, same time, January, 412 ppm. That means despite the slowdown economy, we had higher concentration of CO2. So what is this net zero carbon dioxide? That is what we are talking about. And why should we talk about? Because the current oil production is not going to last long. And, so future energy and material needs have to be, taken from something else. So what is going to happen beyond 2050? Because still there will be crude oil, but that will not be accessed by the current means of production. So the reason for the current economy is the carbon-based economy. Carbon has helped us tremendously over the years. And we are talking about biorefineries these days. But I'm going to talk about biorefinery without biofuel. And this is why, I'm talking with a lot of sense and doing some calculations. My personal belief, and we have presented in this paper, which is cited here, that carbon should not be used as a fuel. So look at the change here. So for example, even by 2050, when we want to achieve net zero, there will be still coal used. So we have to have clean coal technologies. The renewables will go up, so coal will be used. And the outlook for oil demand, it has to come down substantially. So that will be, something like, right now it is about 98 million barrels per day, and it has to come down to less than 20 million barrels per day. Imagine that has to happen. So that means almost 70 million, 70% barrel capacity has to go down. Also, we use natural gas, and in the net zero economy, natural gas consumption also has to go down. Although natural gas is considered to be a near zero carbon economy. So look at the three transition scenarios here. The net zero, where we want to achieve 1.5 degrees C, hydrogen is going to play a very, very important role. And so in country like India, so you can see that, almost by 2050, hydrogen usage will be almost 24% across the world. So what is believed that the renewable energy will increase from current 27% to 51% by 2035 and to 73% by 2050, totaling to about 49,000 terawatt hours. So look at the, renewable energy in power. So net zero is the one which we want to achieve. And this is where, the cost of this renewable energy is going down substantially day by day. Okay, so we know that it could be around 2 rupees, per unit. And so if India's renewable energy target by 2022 is something like, it is said 175 gigawatt, can we produce some energy? So this will be renewable source. So hydrogen is going to be helpful in material, giving the material sources. So on one hand, we want to have more energy, but less carbon. And that is possible only when we use carbon negative energy sources. So I prepared this slide to say that the adoption of green hydrogen technology, and we heard some of them just now, including hydrogen storage. For instance, the ICT OEC technology will add to the might of India's commitment to the Paris Agreement on climate change, to make the net zero emission and to contain temperature rise to less than 1.5 degrees C. So in all these carbon-based fuels, hydrogen is going to be the savior, and we say God is the savior. So how hydrogen is going to be the savior? Look at this. So we already know what is meant by green hydrogen, blue hydrogen, and gray hydrogen. So no matter what sort of carbon you use, whether it is petroleum-based industry or bio-based industry, carbon dioxide is the end result. So we have to valorize carbon dioxide to make net zero. So how do we do that? So this is what is required. So carbon dioxide has to be utilized. So you have to capture it, maybe for power plants, okay, from other sources in the atmosphere, and then you have to utilize it. So how do we do that? For example, currently what is happening about hydrogen? In the refineries, you can see here that there are 8 processes where hydrogen is used, and this hydrogen is coming from steam reforming of natural gas, and the carbon dioxide goes. So this is a gray hydrogen. So when we want to use refinery processes, these are all the processes where hydrogen is currently used. But remember, when we are talking of bioeconomy, again, hydrogen and oxygen are going to play a very important role in biomass conversion. So that means water splitting is the best way of having it. So what we did, we also found out some calculations where 1 kg of crude oil gives 32 megajoule of fuel plus 0.2 kg of chemicals. However, 1 kg of biomass gives only 6 megajoules of oil energy or fuel and 0.8 kg of chemicals. And so this article which we published, it has got something like 4,600 downloads. So what we did, we made calculations to show that if you look at the current refinery processes, something like if you have a crude oil based refinery, you have the production of 215 barrels per second. But if you convert biomass, it gives only 10 barrels per second of fuel. But if you convert into chemicals, it gives 320 barrels per second, and that the value of the product is much higher. So what it means that we can produce a large number of processes which are all based on catalysis, and majority of these processes have hydrogen in there as well as oxygen. So for example, this is 5-HMF. And you can see all these chemicals, which are like benzene, toluene, toluene in the refinery, can be made, including the lignin base, where in the lignin you oxidize and you produce all sorts of chemicals. So in other words, in future, we will be talking about carbon dioxide refinery, where hydrogen will play the role. And what role it will play? So that is what it is. So this is based on our work in ICT, that we take solar power, we also have a molten salt, and this is our copper chlorine cycle. So we take water in that, produce hydrogen, produce oxygen. Hydrogen can be used to methanation of carbon dioxide, so methane and hydrocarbons. In fact, it can be used for waste biomass, including agri-waste, and you can use also oxygen I showed before. And we can produce many chemicals like hydrocarbons, methanol, dimethyl ether, formic acid, formase, syngas, alcohols, ammonia, fuel cells, and whatnot. So these are the 3 projects, which are supported by ONGC. So I must acknowledge them in the very beginning. And so we can have a lot of these products, which are all required. When we have no petroleum, these are the products which will be produced by biomass using hydrogen, including acids and alcohols. And in the so-called methanol economy, which Niti Aayog is also talking, when you convert this carbon dioxide into methanol, we can produce a host of chemicals. And this becomes very important. So much so, the waste plastic can also be converted into variety of products, and the so-called plastic chemical recycling can be done by using hydrogen. So hydrogen is a savior, and I would not talk much about it, but something which was asked, a question was asked some time back in this seminar, is hydrogen safer? So the question is, hydrogen is safer than fossil fuels. You see, look at the explosive energy per volume of fuel. Hydrogen has least. You can see that in other cases, it is very high. And hydrogen is the lightest element. So therefore, even if it is leaked in the atmosphere, it goes away because it is very light in comparison with air, in comparison with you see the natural gas or gasoline. So yes, and in the industrial hydrogen production, we have to compare our technology with the industrial production. Steam reforming, something like 48%. Oil or naphtha, 30%. Coal gasification, 18%. Water electrolysis, 3.9%. And others, like, you have a caustic soda, plants where hydrogen is the co-product. So in future, what we'll have the electricity grid, and we will have hydrogen and electricity conversion. So there will be a hydrogen grid. Okay, and this is where most of the work in the advanced world is being done. So this is very important, because when we were introduced to petroleum and diesel, we had to create petrol pumps and all, so that the infrastructure was required. So hydrogen also will face the same problem. We'll have to create infrastructure. So in the thermochemical water splitting for hydrogen, there are many cycles. There are in fact 216 cycles, and sulfur iodine cycle, BARC colleagues spoke about it. We had also done some work initially, and I will talk about copper chlorine cycle and how we modify this cycle. So this has a huge potential, because what we have found, we can generate hydrogen at 95 cents, per kg without valorization of the co-product oxygen. So far you saw it. Everybody talked about the economics. So how did we achieve this? And what we have done, so this process it involves water splitting. It has a long history and requires much lower operating temperature. Maximum is 530 degrees C. And it demands, material of constructions are lower, and the reactions are perfectly going to completion, and the relatively low electricity, electrochemical soil voltage. So you can achieve higher efficiency and lower environmental impact and lesser cost of the hydrogen. So these are the reactions in this particular case. And you can see the maximum temperature which you can go is up to 475. So this can certainly be achieved by solar power, and that is what we have done. So in our case, so we have electrochemical cell, we have drying, we have hydrolysis, decomposition, and oxygen generation. So this is a closed loop cycle. And we have this plant in ICT. So what we did initially, we produced 25 liters, per hour, then went to 100 liters using the same thing. And we have got several patents in USA, Canada, Germany, UK, Japan, Korea, China, and India. And so there are multiple patents. And so this is a closed loop with solar energy through molten salt. And even we have got a patent on molten salt, because this is a new combination. And our idea is to go for 10 tons per day hydrogen. And ONGC is, kindness is to give me some space in Goa now, not in Mumbai. So we'll soon be going over there. So these are the some of the equipment like spray drying, hydrolysis, a control room, the reactor systems and oxygen reactor. And so we did the energy calculation, because one of the questions people ask is about the energy. How did you calculate? I won't go into the details of explaining it, but just I'm presenting these slides to show you that hydrogen energy, electrochemical reactions, spray drying, hydrolysis, and everywhere we have to devise some new equipment. In fact, we could get patents because of that. In a decomposition reaction, oxygen generation. And you see that, so we did cost calculation of this copper chlorine pilot plant with different production capacity, like 12, metric tons per day, 50, 100, 11, 5, and something like that. And so we could calculate all these things, and you can see that we have got this, something like 0.667. So in the next, slide, it is showing that, actual the calculated cost is about 0.95, USD, and it's the sulfur iodine, which we calculated based on our thing, it is about 1.78. Even if you assume some error in the calculation and efficiencies and all, this is still better than whatever has been reported. So what we did, we looked at the technology maturity of hydrogen production, like steam reforming, biomass gasification, alkaline electrolyzer, which was talked about. And also, so we compared with 19 reported technologies in the literature. Like the steam methane reforming with carbon capture and storage. So you see the feedstock, natural gas, coal, woody biomass, everything else, including algae. And you see, this is the cost of hydrogen, which is given. Assuming these are, these are not, very, very conservative estimate. So something like 1.48 or 1.25. So we based our calculations on that, and we find that ours is something like 0.95. So even if you give some margin of error, this is not going to be beyond anyway $1.5. So this is at the level of confidence. So what we did, we also, you can do the life cycle analysis of well to get of greenhouse gas emissions. So the green hydrogen from renewable electricity is close to zero. So this also fits very well. If a steam reforming of natural gas is 9 kg carbon dioxide per kg of hydrogen. Steam reforming of natural gas with carbon capture and storage with 90% efficiency is about 1 and 56 is 4. And this is based on the natural gas prices in European Union. This data I sourced from International Energy Agency. In fact, the electrolyzers are very expensive these days, and that is the bottleneck for this electrolysis technology. The cost which is available in the literature from the same sources which I got is about $1,100 per kilowatt hour. And it is believed by 2040, it will go down to 220. And so this is very important. So the green hydrogen is anywhere between 1.3 to 2.9 kg. Okay, depending on who is doing it and where it has been done. So yeah, and of course, the solar electricity is to be most competitive for current forcing system. So if the cost of installed PV power can be reduced from the current cost of $5 per watt installed to something like $1, the cost of solar electricity will reach something like 0.1 kilowatt per hour, which is what I showed you in the very beginning. So what is the long-term perspective of hydrogen economy? It is believed by 2030, hydrogen economy will be a reality across the world. Okay, and so very importantly, even the source of energy here, it is said electrolysis from renewable and nuclear will become important. That is what is predicted. So ultimately, they are talking about green economy, so-called bioeconomy using biomass, which I mentioned. I deliberately gave those slides because I wanted people to understand this has a relevance to the green economy, so-called circular economy or bio-based economy. And in all this, green hydrogen will be a very, very important parameter. So conclusion, hydrogen economy can be elegantly intertwined to make many chemicals from waste carbon sources, including biomass and C1 off gases like carbon dioxide. There is a need to develop different hydrogen production technology and to evaluate their impact on energy and environment to meet the net zero goal. Biomass should not be used for production of, should be used rather for production of valuable chemicals and materials and not as a source of fuel. That is what our calculations show. So when we talk about bioethanol, yes, for some time you can go it, but ethanol should be used for making ethylene and all other chemicals. It will be better to use solar energy and other forms of energy, including wind energy or nuclear energy, but not carbon as a source of, fuel. And therefore, Government of India should adopt hydrogen economy to meet the demands of the Paris Agreement. And ICT OEC hydrogen technology, one of the most viable technology, and should be part of a hydrogen mission. That is what I've been saying all these days. So once again, to have the net zero economy, we need hydrogen and we need technology for that. Thank you very much. And I must thank ONGC Energy Center for funding me for last almost 16 years. We have been working in different areas. Thank you. And we're very happy to answer some questions.
Thank you, Dr. Yadav. Now we have yet to go to the last speaker, and I know we are running late, so I'll request INAE that we'll continue up to about 7 so that we can take some questions. And to save time, I note that there are 5 questions in the question answer box. 2 are for, I think, Kalyan Bhanja, 2 are for Professor Ghosh. Maybe if they can type out the answer there itself, so that then we can take more questions there. Okay, so with this now, I think let's go to the next speaker, Dr. Suman Chowdhury. Can I have his biodata, please? Yes. Dr. Suman is a chemical engineer from Yadav University. He received his MTech from IIT Kanpur and PhD from IIT Bombay. And he started his professional career with the pesticide industry and then joined DRDO in '94. Right from the beginning, he has been working on phosphoric acid fuel cell along with onboard hydrogen generators, power conditioners, battlefield power bringers, etc. He, along with his team, have developed and industrialized the PAFC technology for materials to stack engineering, leading to complete power plants with onboard methanol reformer and hydrolyzer-based hydrogen generators. The fuel cell power plants developed by him and they range from portable, less than 100 watt, to 350 kilowatt systems, a wide range, less than 100 watt to 350 kilowatt systems for various defense applications. His current research interest involves futuristic EIP system, large capacity flow battery, and process intensified reformer system. And of course, he has published several papers. Over to you, Dr. Suman Chowdhury.
Thank you, sir. Good afternoon, everybody. So let me straight away start the presentation. I hope the slide is visible. Right, sir. So I have two parts of the presentation. One part is about the perspective of hydrogen energy. This is based on our 25 years plus experience because we have developed, industrialized, and deployed many fuel cell solutions. But although many of the solutions of green energy, etc., is known for quite some time, but it has still not made a good headway, is because of certain reasons. And my first part of my presentation will be to focus that, to put things into perspective as per our understanding, and to say how we can focus, rather refocus the technology development tools, rather technology developments and the performance parameters of them. And the next part is about some of the items what we have developed, that is, which can also have dual purpose use. So, just 1 minute. Yeah, sorry. So, although we love to hear that hydrogen energy is required, but the world doesn't think like that. Particularly India, they want a clean, sustainable energy with energy security, with affordable pricing. So if you see various type of primary fuels and energy sources, solar PV and solar derivatives like wind, etc., has to fill in the gap of the fossil fuel because hydroelectric, nuclear, and geothermal has limited scope in our environment, in our system as of today. So if the system is dilute, there is a question of separate assessment. If the system is dynamic, even dilute is okay. If the system is dynamic, that is, it has a different output at different time, then we need to manage it in a different way. And there where the hydrogen may play a role. If it is uniform source, even if it is dilute with existing power conditioners, etc., we should try to put it directly into the grid. So now non-uniform sources energy storage mechanism, what we mean is that, for example, India needs already, it was mentioned by Dr. Grover, about 1,600 terawatt per year. And we can definitely generate about 800 to 900 gigawatt of solar power. So that is sufficient to meet at least a very major chunk of the future production also. But we need to manage about 3,000 to 4,000 gigawatt hour in a distributed manner. Where is the technology? That means when the sun is radiating, you can make the hydrogen, or make a storage device to store the energy and then take it into the lean time. So for that, today's technology, there are not many options. This is where exactly the hydrogen can fill in. And this is the opportunity, business opportunity, because there are many limitations of hydrogen energy. We all know that. And it is not going to go away because many of the fields are quite mature. So the operation window or the opportunity exists through this renewable, when the renewable is much more than its regular consumption, not 2%, 5%, but maybe 70%, 80%, then only perhaps hydrogen energy will get its due. Now, the first part of hydrogen energy, which many people have talked, gray hydrogen, blue hydrogen, all those things, we have deployed them. We know that actual power, tank to wheel power efficiency does not change beyond 20%. And with such low margin, the cost and complicated technology implementation for the commercial world, especially a country for India, it is very difficult, and perhaps that is the primary reason it has not gone ahead. The other option, that is a total green, that we are using through solar PV based hydrogen energy as a storage media only. Just remember, as a storage media only, there lies the opportunity. I'll try to explain how. So in our concept of hydrogen grid, we have a generation system, exploitation, transportation, and stabilizers. Efficiency is the primary key for hydrogen generation because you have to save the hardly owned, the solar energy. And competing technologies like direct photolysis also need to be considered. And for India specific, I will elaborate it later, why hydrogen halogen systems are very, very useful. And for transportation, you need high pressure hydrogen compressors, solid state compressors, not normal compressors. For example, for defense purpose, for underwater use, we have developed an electrical compressor up to 300 bar. And it consumes electricity almost similar to its thermodynamic calculation value. It is so very efficient. Then it needs stabilizers. That means if such a big rate, suddenly there's a drop in hydrogen, you need to generate some amount of so-called blue hydrogen. Through dimethyl ether is a very good option. And any other thing like methanol or even fossil fuel. So when we talk about exploitation, hydrogen, oxygen, or air fuel cells are pretty costly. Every year the cost is coming down, but it has still some more to go perhaps. Other option is this again, hydrogen halogen fuel cells, which can be a game changer for India if correctly deployed. So now let us see about the technology configuration and the performance markers. When we do water electrolysis, typical electrolyzers at significant good current density, not at a few milliampere per centimeter square, you will need about 2.0 volt with respect to 1.3 volt. And when you consume this in fuel cells, typical acid fuel cells like PEM and others, 0.75, even 0.8. That means 38% only. So your primary research should be, if you're developing electrolyzer, it should be less, around 1.6 to 1.7 volt. One of the options is to develop this HER type of catalyst. There are many technologies that is coming now, but we need to focus on that. Direct photolysis up to 5% with water separate, with hydrogen oxygen separation through cathode and anode is already demonstrated, but still it needs to be 7% or more. Otherwise, it will be very similar to normal PV with 2 volt operating electrolyzers. Now we'll take a look at solar PV electrolysis scenario where it would be hydrogen chloride, you are electrolyzing, or hydrogen bromide, whatever it is. Hydrogen bromide is better kinetically. You will have 1.36 volt thermodynamic and electrolysis of 1.6 volt. And if you use it in hydrogen chlorine fuel cell or hydrogen bromine fuel cell, as the case may be, it will get about 1.0 volt easily. So that means you will be developing about 1.65 times more efficiency than normal electrolyzers. So this is a system, a rather low-hanging fruit, not very low-hanging, as I'll tell you why later on, need to be focused. Once upon a time, these electrolysis and hydrogen halogen fuel cell were at par with hydrogen oxygen fuel cells. Later on, it was dropped by the Western media due to various reasons. But now this provides us a very good window of opportunity for India. Okay, so if we focus, technology focus, green hydrogen generation, efficient electrolyzer, water electrolyzers, direct photolysis, and hydrogen halogen cycles. Transportation, you need compressors because you have to transfer through pipelines mostly, that otherwise it will not be cost effective. And exploitation, primary thing is platinum, total reserve. If you see, after take it out of for pharma, etc., it is not sufficient. Even it will be difficult to plug in, say, 5 million cars. So you have to have non-platinum catalyst for oxygen reduction for acid media. Another option is for alkaline fuel cells, which is thermodynamically very good, but plagued with corrosion issues. We can easily use nickel or other kind of things which need to be checked in, like the Russians. And of course, halogen fuel cells allows you different type of chemistry, different type of catalysts. So this part, perhaps I can skip because this is about existing technologies. With existing technologies, there is a dire need to put up certain industrialization, do certain startup companies, and put it into certain campus to run it like hydrogen park. Otherwise, you cannot tune the future systems. Okay, this everybody knows. I'll just skip this. Now comes the this proposition. I will perhaps comes later. Sorry to place the slide wrongly. So now let us go to the defense use. Defense use parameters are totally different, but I will try to explain. Some of the tools may be useful here also. For NMRL, we mostly look for field power, distributed power, and all electric ships and air independent propulsion, which is basically a submarine power. Now, sorry, I think I am going back. Yeah. So this is where we focus. We try to see which kind of fuel or material can carry maximum amount of hydrogen with respect to its volume, with respect to its weight. This is definitely not the way we look for commercial use, but for defense use. We don't bother environment pollution at this stage, but we see which has the most intensified. So we have this borohydride and also borines and reformed methanol. These are the three things we have found it very useful. Reformed diesel, we did some experiments of work, but not very suitable right now. Okay, other type of things, carbon nanofibers, some novel materials that I'm leaving out because that is the technology readiness level is not there. So when we come to the contribution, almost 25 years we are in this field. Phosphoric acid fuel cell, we have completely developed and industrialized all the materials and the complete stack system, and also for mostly for defense use, land-based, and other thing is for marines, which is highly hardened. And almost a 1 megawatt equivalent of stacks has been produced by the country, various industries. And 100 watt to 300 kilowatt power plants are being made with power, complete with power conditioning, which is a very important part to manage the microgrid and the power managers. So this is what we have done. But what are the things? These are in the around 2007, 2008 to 10. We developed this onboard methanol reformer-based fuel cell systems. It is a little costly for commercial use, but definitely it proves very good in the Himalayan ranges. And right from 2.5 kilowatt hour, 2.5 kilowatt to 10 kilowatt, even 15 kilowatt, we have deployed in various places, mostly for land-based use, for defense purposes. Then sometime back in 2006, we did an experiment with Reva. That time Reva was not yet taken over by Mahindra. They gave us a pilot vehicle. We tried a range extender fitted with a planar methanol reformer, which you can see at the onset. And of course, from there, the reformer technology we have improved manifold. But even then, if we find like what Mr. Elon Musk is talking right now, that perhaps electric vehicle is for the battery rather than the fuel cells, we also believe the same way and left that path. Maybe we are wrong, I don't know. So now this is perhaps about that all the type of systems that we have deployed. This is the jewel in the crown. Unfortunately, I cannot talk much about it, but this is a plant which sits in the submarine, and when she is underwater, provides the power, a very high amount of power. And this is a technology where we are one of the technology leaders in the world. And what allows us to do that is absolutely in-house developed phosphoric acid fuel cell, and there's borohydride cracker technology. Okay, now let us talk about, sorry, I went ahead. Yeah, this is perhaps a very, very useful thing. That is a flow battery. Somebody call it flow battery. We call it halogen FC, or whatever it is. So there are two parts. We are not trying to develop a regenerative fuel cell. Like in the past, it is very difficult. So what we are doing, this is mostly we are targeting for an army unit, which is stationed at a place, and they are trying to do energy harvesting to reduce the logistic line. So you can have a membrane, microporous, Teflon-based, or even Nafion type, different combinations we have tried. Hydrogen bromide is the best we have found for kinetics-wise. So you generate, use the solar power, use hydrogen and bromine, and that you use in a fuel cell like device. We are using the anode is of course semi-noble, and the cathode is of course, so we have a mesh metal that we are not able to discuss right now because we are here to take any patent or publication. So the idea is to develop for defense purpose. First target is about 50 megawatt hour and also to 150 megawatt hour. There are two variants, and later on we may go for 1 gigawatt hour. But cost wise, we don't know as of what will happen at that kind of level of values. But one thing we can tell you that it is giving us about, not even 65, it is giving us about 70% overall efficiency from the energy that is the electrical energy from the solar power units to the final what is get by the user, including certain parasitic loss. So it is a very good technology, ladies and gentlemen, that which we are focusing now. And now I will, before ending my talk, I will perhaps go to my proposition. See, there are different technologies that is possible. Many speakers today have also elaborated that. But the thing is, you need to choose. And you need to choose and consolidate, you need to quantify the complete powertrain, that is tank to wheel, not a simple small block. And that is what there is a need to publish a paper. If you remember some time back, quite a time back, there is a hydrogen energy roadmap, but that is very qualitative. We need our researchers to sit together, various experts, and impartially arrive at various technology options, put what is the overall competitive level, that is what should be the efficiency, vis-a-vis what is the conventional ones, that is what are the competitors, so that we can do a SWOT analysis, that is strength, weakness, opportunity, and threats. Then if we do that, and also we see whether we can make it, okay, it is a good thing, but can we do it? That is deployment level, technology readiness level, and feasibility within India to do it, or maybe with some support from abroad. So those are the things, and then comes the identification of possible agencies. So if we have this kind of report, then only perhaps the policymakers could put their funds judiciously, and we can, make a good thing out of it. Otherwise, it is going in a very similar way, unfortunately, to talk like this. The solar PV. Long back, I used to see NMRL is giving a lot of fund for solar PV. Ultimately, when the solar PV technology happens, mostly it is foreign. That should not happen with us. And definitely hydrogen energy and renewable goes hand in hand. Unless we have extra and renewable power on one hand, maybe hydrogen energy will not make its way. That's all, ladies and gentlemen. Thank you for listening.
Thank you, Dr. Chowdhury, for taking us through a range of technologies developed by you and your team in DRDO. And I take note of your recommendation that INAE should bring out a comprehensive report, and with emphasis on indigenous technology development, which departments like DAE, DRDO space have always advocated. I think we had 6 very good presentations. It's a very, very sort of happy feeling to note that so much of work is going on developing technologies related to hydrogen. And we have already overshot time, but we'll definitely take up the questions which are there in the chat box already. Earlier I noted the 6 questions. Yes, they are there. First 2 are for Mr. Kalyan Bhanja. First one is, Kalyan Bhanja, are you there? Can you please inform us about the lifetime of each of the electrolyzers? Unmute yourself.
Yes, sir. Yes, sir. So if we talk about this alkaline water electrolyzer, typically for cell module, it will be minimum 5 years. And for balance of the plant, it will be 10 years as on today, but it can go beyond that. Balance of the plant, it can go even up to 20 years. We have not run up to that value, but definitely it is more than 10 years. And cell module, definitely 5 years.
5 years.
Yeah.
Okay. From the same participants, it is Sarita Vishwanathan. There is another question. Can you also share information on quality of alkaline water or water required for hydrogen production?
Sir, it is less than 2 microsiemens per centimeter. That is good enough. The DI water, no? So if it is less than 2 microsiemens, that is good enough. Otherwise, this is some issue with this basically some hardness problem, because there can be some issue with that. Otherwise, as such, lot of KOH is there. It should not be a problem. Only it should be less than 2 microsiemens per centimeter. That is good enough.
Okay. And the next two questions are again from Sarita Vishwanathan, and they are for Professor Ghosh. First one is, what is the amount of platinum required per battery? Professor Ghosh, please.
So for our case, actually, we are trying with 0.4 mg per centimeter square. That's what I was calculating total, that you will be requiring around 1 gram per kilowatt at present, whatever it will be.
Okay, next question for you is, can you please inform on the safety required in the use of vehicles? A safety issue will become important when we use hydrogen in vehicles. What is your comment on that?
Yes, of course, when hydrogen comes into picture, always we talk about the safety, but always also we are dealing with LPG at home every day. And if we compare with hydrogen and LPG, there are lots of literature to be finding that probably hydrogen is much safer than LPG, because even if you catch fire, actually hydrogen will be above your head, but LPG will be actually on the floor, you cannot run. So there are lots of advantage as well as for hydrogen in terms of safety, but there are lots of other myths about that particular accident happens. So people think probably hydrogen is very dangerous. Of course, it's safety has to be taken definitely, but it's not that dangerous like also like other fuel you are using at home. Also, it is like that also, so it's not that dangerous in the vehicle as well.
Thank you. And next question is a general question from Dr. R.K. Singh. What is at present cost comparison in terms of dollars kilowatt hour between various design of fuel cells in terms of well to wheel, as it is often quoted as a true measure of engine performance? Maybe Professor Yadav, you will like to take up this question? Professor Yadav, please, will you take up this question, or I think you have to unmute.
Okay, sorry. You know, the well-to-wheel analysis which is done by the International Hydrogen Council. So that is what I was talking about. They say that the cost of hydrogen fuel cell will come down, and so in that case, for example, they said the renewable hydrogen, obviously, it is electric. This is greenhouse gas is zero. Steam reforming is with natural gas is 9 kg carbon dioxide and about per kg of hydrogen. So that cost is added to that. And if you take carbon capture, then the cost goes up. But as far as wheel-to-wheel analysis is concerned, I don't have an exact number with me right now. Okay, I'll have to look at it.
Okay, I think we go to the next question. It is from Venkat Murlidhar. It is shown that very huge amount of hydrogen can be stored in just 125 milliliter volume. In case of any mechanical failure, what are the energy release rate and shock propagation rate? I think Dr. Sudarshan, will you like to take it up? Dr. Sudarshan?
The hydrogen storage capacity of the Ti2 CRV alloy is around 4 weight%. So, and if you hit that 4 weight% at room temperature, and subatmospheric pressure, we can store around 144 liters if you have a 300 gram of the material. If you have around 300 gram of the material, we can store around 144 liters. The temperature generated are not much. It is around 50 to 60 degrees centigrade only.
Okay. Okay. Now I think any of the panelists have questions to each other. We take up that now, and there is nothing from the audience at this moment.
Sir, I am Chowdhury. I wanted to clarify further about the last question. If I understand the question correctly, it is see nowadays they are trying to store hydrogen in glass and that kind of metal balls. It is purely a storage. So that kind of thing is glass is fused and then the hydrogen is put in, and then once it is crystallized, it doesn't come out easily.
Okay.
So for that, the software does not come, because if some it is impossible to get cracked all the balls together. These pebbles are very small. It's a fine bits of thing. So then the shock propagation, it is almost safe from the shock propagation. That's why I want to add.
Okay. I think Venkat Muralidhar has a further question. Also, here several methods for hydrogen productions have been shown. However, the viability varies. In extractive metallurgy, pyro-hydroelectro routes could be used for some metals. However, not all are viable economically for all metals. Similarly, we have to decide on best viable routes for hydrogen production, thermochemical or electrolyzing routes. Yes, this is something, this is a good comment, and that has to be decided. I think Professor Yadav presented a comparison of various methods. Different other users have given cost of whatever they are doing. Best method, of course, will always prevail. Now I see Professor Suresh has been all there right from the beginning. Do you have any question, Professor Suresh, before we close?
Yeah, no, I don't have it.
Okay, okay. Shashwati Rai, over to you now to close. I think she's not there, or well, I think we had a Shashwati, yes. Yes, this is another question. What is this now? There's a question in chat box. How much kilowatt hour can be produced by 1 kg of hydrogen by PFC or PFSC? How does this compare with energy required for producing 1 kg of 2? I do not know, this question is not very clear. 1 kg of hydrogen. How much kilowatt hour can be produced by 1 kg of hydrogen? How does it compare with energy required in kilowatt hour for producing 1 kg of hydrogen?
Can I take that question? I have also understood partially.
Yes, please go ahead.
See, the hydrogen has, the delta G of that amount of hydrogen is always available to you, provided at what potential you are extracting the thing. If you're extracting at 1.23 volt, then you will be able to do the exact delta G equivalent that you can calculate. But generally, it is 0.75 to 0.8. Typical PFC or PMC, it is not very different. So based on that, if you calculate, I think you get about 50% of the energy with respect to delta H and 60% with respect to delta G. You can calculate for this.
Yes, okay. I think we are now going close to 7 when we should stop. It was very interesting to note that so much work for development of technologies is going on in the Mumbai region itself. I think if we look at the country as a whole, much more work must be going on. I think thanks to all the speakers, and over to Dr. Shashwati Roy.
Yeah, I also join you in thanking all the speakers, especially today was a very difficult day for Mumbaikars. So even with all these things, everybody was on time and they have given their best. I sincerely thank all 6 of them. And I also thank Dr. Grover for handling this difficult session so efficiently. And thanks are also due to the audience, because such a huge participation was there. Till some time back, around 100, more than 100 people were there all throughout the sessions. So thanks a lot to the full audience, and additional thanks to our council academy for giving us the support. Till from the beginning itself, they have supported us. This our Colonel Rai and his team. So with all these things, we close. Thank you again, and we'll come back with a very interesting topic with Professor Shri after 2 months, maybe in month of August. So please be with us. Thank you.